And now it is my pleasure to introduce our following speaker, who well, as you've seen, we've had a very international collection of speakers today, and we have an in-house speaker from Ucraft, our first speaker from Armenia. We have the Vice President of Engineering at Ucraft, Tigran Mesropyan. He will share with us a speech about distributed architectures for microservices craftsmanship. Please join me in welcoming to the stage Tigran Mesropyan.
Thank you. Hello, nice to meet you. My name is Tigran Mesropyan, and I'm the VP of Engineering at Ucraft. Today, we are going to talk about distributed architectures for microservices craftsmanship. But before diving deeper into distributed architecture, let us have some kind of recap about what is microservice design pattern and what are microservices in general. So currently the word microservice is already a well-known term in the technical industry. That means that the whole project consists of different components that are self-deployable, self-upgradable, and self-replaceable. The components that can function as a standalone programs. Here are some benefits of microservices over the monolithic architecture. Here we can see that it has strong boundaries, and because the system consists of different components, there are already defined strong boundaries and encapsulated areas. Deployment sometimes can be independent, and the technology can be with different programming languages and with different technical stacks. People management also can be easy in this case because different people or different teams can work on different platforms without interacting with each other. Microservices are easy to test. They have better scalability, easier maintenance, and fault tolerance capabilities. Now there is a question. Should we start with microservices or not? And there is a common pattern that one should start its project from the monolith, make it modular, and continue to develop that monolith application until it will become harder to maintain. And whenever it will become harder to maintain the monolith application, it's time to divide it into microservices. This sounds great, but unfortunately, this approach doesn't work in most cases, especially when the monolith is already in live and your company has real customers that are using your monolith application. In that case, the company should divide two teams. One team should maintain the existing application and another should maintain the refactoring process. And because requirements tend to change, the customers will want to see new features in the existing application. And the refactoring team will always lag behind and try to catch up with the team that is handling the real project maintenance. That's why it is better to start with the microservices at first if your company wants to have a microservice environment. But unfortunately, again, there are other issues that are related especially to the microservices patterns. And today we are going to talk about them. So the first one is code duplication. This problem is partially solved if all the microservices are written in the same programming language. But in case there are variety programming languages used in the microservice environment, it is hard to skip the code duplication or logic duplication. The another part is communication and message passing, which is related to the topic how to communicate different microservices with each other and how to make them talk to each other. And the last one is data sharing challenges and strategies, which is related that how should we share our data between our microservices. Now let's talk about communication and message passing and define what is programming from this perspective. From this perspective, the programming is an elegant way of management of data transfer between different areas. And yes, in general, programming means to transfer data. And whenever we are switching on our computers, the BIOS starts to load our operating system from hard drive to the RAM. And after that, operating system starts to load various programs that will make our computer to work. And under the hood, everything is transmission of different bytes and bits that are making our computer to work. And the same is for programming in general. Now let's see what kind of communication patterns we have. In general, there are two types of communication patterns or techniques: synchronous communication and asynchronous communication. And the most common synchronous communication is the network call, perhaps the RESTful API or REST, when one microservice sending API request to another microservice. But this approach can consume a lot of time, especially when those requests are much during the workflow. So we should avoid synchronous communication as much as possible. The exception cases are when we need real transactional consistency. Only in that case we need to use synchronous communication. Now let's talk about asynchronous communication. Can you please change the slide? Thank you. So there are two types of asynchronous communications: orchestrated communication and choreographed communication. Now let's talk about orchestration communication. The orchestration pattern uses an orchestrator or mediator who is responsible for maintaining the state of the workflow, error handling, notification, and a host of other workflow maintenance. Here in the picture we can see that we have service A, service B, and service C. All these services are not aware about each other. And the only service that maintains the workflow and transfers the information is the orchestrator. In this case, error handling, state management, and information transfer is handled only by the orchestrator. Here are the benefits and also drawbacks of the orchestration pattern. So the pros are the workflow is centralized, the error handling is much more easy, it can recover from the error states, and state management is centralized. But there are also some drawbacks, as we can see here. For example, responsiveness, fault tolerance, scalability, and services are coupled together because they are structured around the orchestrator. The next one is choreography communication style. The choreography pattern visually illustrates the intent of the communications where partners communicate with each other like it is done in the dance partners. So here we can see in the picture that service A sends message to service B sends message to service C, and service C sends message to service D. So there is no orchestration and there is no state management. The bad part here is that whenever there will be some kind of error condition, for example, if something will be broken in service C, so service C should notify about that service B, and also it should notify about that service A. And both service A and service B should handle that error condition by their own. So there is no centralized error handling mechanism with this design pattern. Here are the pros and cons of the choreography pattern. So it is responsive, scalable, fault tolerance, and services are decoupled, but there are also disadvantages, like workflow is distributed, state management, actually there is no state management, error handling is harder, and also recoverability is harder. Now I want to tell you a little case study about Ucraft and how the migration process is working at Ucraft. So, what is the migration at first? Migration is the process of controlling the database versions. At Ucraft, we are running tens of thousands of websites, and every website has its own single database. And during the development, there are cases when we need to change something in the databases, and that change should be affected on the existing websites as well. It is impossible to do that migration in a single shot. That's why we implemented our own migration workflow, which is orchestrated-based workflow. And here we have a migration dispatcher, which is our main orchestrator, and we have a migrator service, which is responsible for migrating the real websites. And whenever a website sees that it needs to get migrated, it sends message to the migration dispatcher, like something, hey, please, can you migrate me? And after that, migration dispatcher sends this message to the Kafka topic, to the message broker, and the migrator consumes that message and starts the migration process. In case of success, it notifies the migration dispatcher that everything went smoothly, and that again notifies the website that you are already migrated. In case of error, again, migrator notifies the dispatcher that something went wrong, and here dispatcher can decide whether it should retry the migration process or somehow notify the owner of the website that something went wrong during the migration period. As we talked about Apache Kafka and message brokers, now let's see what are message brokers in general. So message broker is a piece of software which enables services and applications to communicate with each other using messages. This allows applications to share information with each other, even if the applications are written in different programming languages. And how do message brokers work? There are three participants in this game: producer, consumer, and queue or topic. Producers are the applications that are responsible for sending messages, and consumers are the endpoints that are receivers of those messages. And the queue or topic is something like file system or folder where the message brokers can store data. Here is the pros of message brokers. So communication between services that may not be running on the same time. For example, producers can produce messages into the topic, and after that go down or go idle, and after that consumers can wake up and consume those messages. So this provides the improved system performance by introducing synchronous communication capabilities. Another advantage is increased reliability by guaranteeing the transmission of the messages. All the message brokers have possibility to retry to send the message in case of some kind of failure, and messages can stay in the brokers for a long time. That means it is impossible to have a data loss. Here are some cons of message brokers, like for example, the system becomes complex when we are integrating message brokers, and it requires a steep learning curve, and sometimes debugging can be harder. Here are the list of maybe most famous message brokers like RabbitMQ, AmazonMQ, Apache Kafka, Redis, and Amazon SQS. Now let's see some case studies again how Ucraft is leveraging Apache Kafka. The first example is how Ucraft is tracking actions. There are various actions that are happening in the Ucraft websites, and we are tracking those actions for creating analytical and activity reports. And here we can see that various API sources just need to produce some kind of messages to the Kafka topic, and then the action tracker service, which is responsible for tracking and storing those actions, will consume messages from Kafka topic and will store them into the Elasticsearch. After that, our analytical and report generation service will load data from the Elasticsearch and will generate the reports. The next is how we are running background tasks. All we know that in web industry, long-lasting tasks should be run under the background. So here we have special workflow for that. Again, various sources can produce messages to the Kafka topic that are related to the background tasks. And the command bus, which is responsible for running background tasks, will consume those messages and start to run them in the background. The next one, how we are collecting our searchable data. Because we are a website builder and an e-commerce website builder, there are cases where we need to have our own search engine. For example, when our customers want to search for products or for blog posts. For this reason, we have another workflow. So various sources that need to store something as a searchable content should produce those messages into Kafka topic. And the collector, which is responsible for storing those data, will consume those data from Kafka topic and store them Elasticsearch. Later on, our search engine will retrieve that data and provide search availability. Another one is how we are sending emails. Again, the same workflow, different APIs or microservices can send various emails under different circumstances. All they need to do, they just need to produce message to the Kafka topic. And the messenger microservice, which is responsible for sending emails, will consume those messages and send an appropriate email. And last but not least, our notification sending mechanism. Again, various APIs can send different kind of notifications. And all they need to do is just produce message to the Kafka topic, and the notifier, which is responsible for sending notifications, will consume those messages and send them to their receivers. Now let's talk about data sharing challenges and define what is programming in terms of data. So programming is an elegant way of storing and sharing data. The data should be stored in a secure place and should be easy and fast accessible. In most monolithic systems using a single database, developers never think about how to store and share data because it is possible with one single command to load a bunch of huge data. But when data is divided into separate places and owned by distinct services, it is very hard to load a bunch of data from different places and combine them together. That's why there are different patterns for data access. And today we are going to examine these 4 patterns: inter-service communication pattern, column schema replication pattern, replicated cache pattern, and data domain pattern. So what is inter-service communication pattern? This pattern is by far the most common pattern for data access. If one service or system needs to read data that it cannot access directly, it just asks it for data to the owning service. Here we can see that we have our product service, which holds product information, and we have order service, which holds order information. And whenever order service needs some kind of product information, it just simply asks to the product service for that information. Here are the pros and cons of this pattern. So this pattern is simple and there is no data volume issues because data is stored in a single place. And cons are network data and security latency because whenever we will need some kind of data, we need to do a network call. Scalability and throughput issues here are also because in case of product service will go down, that will mean that the order service is also down because it cannot connect with the product service. There is no fault tolerance, and this approach requires contract between these 2 communicating services. Another one is column schema replication pattern. With this pattern, we just need to replicate the same column in 2 different places. For example, here we can see that the product service and order service are independent and they are not connected with each other. And in case the order service needs something from the product service, like product description in this case, it just stores that part in its own database. So 2 different microservices that are holding 2 different databases, but the column is replicated in 2 databases. So here are the pros and cons of this pattern. So first, it is good for data access performance, and there are no scalability and throughput issues. No fault tolerance issues, and there are no service dependencies. But there are also other disadvantages, like data consistency issues, data ownership issues, and data synchronization is required. In case the data will be not synchronized, that will be a data consistency issue. Another one is replicated caching pattern, which is based on the standard caching pattern. In this case, every microservice holds an instance of a cache, which is replicated with other microservice cache, and together all the replicas are sharing the same information. So here is the example of a single in-memory cache. So each service contains its own unique data, hence there is no data is shared. So we can see that service C, service B, and service A both have their own instances of the cache. And then another approach is distributed caching. In this approach, there is a standalone caching server which holds the shareable information, and three services like service A, service B, and service C are communicated to this server, and they are sharing data between the caching server. And here is the replicated caching again. So here we can see that we have three services that all have their own instances of the cache in their memory, and the cache is distributed together. And if something will be changed in the service A, that change will be distributed to the service B and to the service C, and the same for other two services. There is one note that not all caching vendors provide the distributed capabilities. So we need to be, first of all, we need to check before we are going to use some kind of distributed caching system. And here is the replicated caching in action. So we can see that this product service and order service again both have their own instances of the cache, and the cache is distributed between those two services. And here are the pros and cons of the replicated caching pattern. It is good, provides good data access performance. There are no scalability and fault tolerance issues. Data remains consistent and data ownership is preserved. But it requires cloud and containerized configuration. So in general, it is hard and complex task to set up a replicated or distributed cache. It is not good for high data volumes because data should be replicated in different places, and also not good for high update rates, because if update rates are high, then the synchronization process, in that case, we will have a data inconsistency. And the last pattern is data domain pattern. With the data domain pattern, tables that are shared within different microservices are combined together in the single schema or single database. Here we can see from the example that the product service and order service are connected to the same database or schema, and that holds both orders data and products data. While the sharing of the databases is encouraged in the microservices area, this pattern really works and have a lot of benefits. Like, for example, it is good data access performance. There are no scalability and throughput issues, no fault issues, no service dependencies, and data remains consistent. The only issue are that the broader context is owning the data, and there are more security points and data ownership governance. Now let's see our last case study about URL management at Ucraft. There are various services at Ucraft that need to have an access to the URLs of the websites. Here are those services. For example, our website service, which requires URLs to render the pages. E-commerce service, which requires URL to render the products and categories. And sitemap service, which requires URL to generate the sitemaps for websites for SEO applications. And there was a problem, and there is a need to share a piece of data between different services. And best solution for us was to use a distributed cache, so the different services will gain access to the same data through the distributed cache. And here we can see that sitemap service, e-commerce service, and website service both are connected to the same cache instance, and they are both receiving and can read the same data. And in conclusion, I want to mention some thoughts from my speech. So at first, it is better to start with the microservice application from the scratch if you want to have a microservice application. And when we are starting with microservice application, we need to, and during the period when we are defining the architecture, we need to concentrate about patterns that we are going to use for data sharing and patterns that we are going to use for data transferring. And the distributed architecture can help us to establish complex, reliable, fault-tolerant, and scalable applications. Thank you very much.
Thank you so much, Thank you so much, Tigran. All right, we are early on schedule, which is always a good sign, and we can now move into the question and answer period. Here's the QR code for you. Any questions that you have for Tigran, please submit them. Tigran, we'll see the questions come in very quickly.
Thank you.
Where did it go?
Which one I should answer?
As you wish. This one maybe, because it has a vote. Would you like me to read it?
Should I read it or just answer?
Go ahead and read it so people know the question.
Okay, how do you deal with excess of hosting web pages requiring high computational power in background, like using AI models? So, in general, we are not using AI under the hood for generating web pages. We are using AI for generating websites which are not under the hood, and we are using them in the real time. For example, our AI engine can read the prompt of our merchants and based on the prompt suggest them ready websites. And those computation is not going in the background, it is going in the real time. So under the background, we are just using some kind of data gathering processes for our AI.
Thank you for the answer.
Ucraft uses gRPC, yes. Ucraft uses gRPC in some places. Have you ever faced any authentication and authorization issues between microservices? Any insight how to address those? Yes, there is an issue related to how to authenticate and authorize communication between microservices. In our case, because we have our own single sign-on server, which is our identity manager as well, all the requests, no matter are they gRPC, REST, or communication by message brokers, if they require some kind of authentication or authorization, they are traveled through the SSO. Or the microservice can check the request with the SSO, is it authenticated or authorized to do that action. What are the implications of a rapid increase in the number of services and what potential solutions can be considered? I don't see here any kind of implications. If we have a defined architecture and our microservices are connected with each other by some kind of contract and everything is defined beforehand. So first we are defining the architecture, then we are introducing a new microservice. Everything should went smoothly. So there are no any kind of errors or. So the solution is to, first of all, so it's the general solution. First of all, to structure how the communication should be and how the data should be transferred between microservices. I guess that's it, or?
No, there are a few more. Yeah, you can scroll down. We still have time for Q&A, so go ahead.
In what places are you using gRPC? To replace Kafka? Not. gRPC cannot replace Kafka. In general, under the hood, Kafka is using RPC as a data transfer medium, but we are not using gRPC to replace the Kafka. In cases where it is possible to replace REST with gRPC, we are using gRPC, because gRPC is using HTTP2 protocol, and it is pretty much faster than REST that is based on HTTP1. Because in our case, there are some kind of programming languages that don't support gRPC. In those cases, we are using REST. But in cases if the language supports gRPC, we are using gRPC. For example, all our AI microservices are talking to each other with only gRPC. There are no any kind of other communication. What is a good practice to do with documentation when business logic gets distributed across microservices and distributed tracing does not exist in the application, so debugging is difficult? Yeah, very good question. Yeah, in case of what is a good practice to do with documentation when business logic gets distributed across microservices and distributed tracing does not exist in the application, so debugging is difficult? Actually, when project becomes larger, the documentation is a pain in the neck. So with this approach, I would say that it is not a good practice to document everything, because whenever someone will write those documentation, maybe that microservice will be refactored or will be removed from the system. It is better to have some kind of charts or diagrams that will show how the system is working in general. And the code should be written in a self-documented way, and there should be only small portions of documentation that are describing the general workflows. But it is impossible to document everything in the microservice term, in my opinion, because everything changes during the development. How to avoid microservices hell? So first of all, again, everything is based on the communication. If you are facing a microservices hell, that means that the requirements and responsibilities of the microservices are not defined clear. So it's not the thing that everything that is a single job should be deployed as a standalone microservice. So first of all, there should be defined actions and actors, and how actions and actors are communicating with each other, and how that everything is related to the domain of the project. And based on that research, the most common actions should be placed together in one microservices. And sometimes the data sharing can also introduce a need to merge two microservices together.
One more question.
One more?
Just one more, and then we're out of time.
In which cases your conclusion will not apply? Maybe the question is about to start with microservices from scratch. If that's it, the question, I guess if we are not planning to use microservice, in that case, my conclusion will not apply. But if we are planning to use microservices and we already made that solution, so in that case, we need to start from microservices. But in case the project is small and there is no need to divide it into microservices, in that case, there is no need to divide it from the scratch.
Thank you so much, Tigran. Forgive me, that's all the time we have.
Thank you.
Join me in thanking Tigran Mesropyan from Ucraft. Ladies and gentlemen, thank you for your time, Tigran.